Hello everyone, welcome back to my videos on discrete mathematics and its applications. Now we come to the next part on our discussion of relation, and this time we will be talking about equivalence relations. So equivalence relation uh, is a relation that satisfies a property of equivalence. So equivalence is a property of binary relations like reflexive, symmetric, and so on. And in fact, given a binary relation R, we define R as an equivalence relation if R is simultaneously reflexive, symmetric, and transitive. So R is an equivalence relation if R is reflexive, symmetric, and transitive. So uh, if these three properties are satisfied by R, then we would say that R satisfies the equivalence property. Now, if the pair A comma B is in R and R is an equivalence relation, then we usually call A and B equivalent. So these two elements of A are equivalent. And we often write with this symbol A and then a curly like symbol or like a tilde and then B. If the relation R is clear from the context, we simply drop the subscript R. So you just write A and then tilde B. Now let's continue with an example to clarify this definition. So suppose you have two relations R1 and R2, both a binary relation defined on the set A with elements with integers 1, 2, 3, and 4 as elements, where R1 is defined to contain these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pairs of numbers 1, 1, 1, 3, 1, 4, 2, 2, 3, 3, 3, 1, 3, 4, 4, 1, 4, 3, and 4. And R2 is just R1 union 2, a set containing two pairs 2, 4, and 4. Now determine if R1 and R2 are equivalence relations. So let's start with R1. So how do we determine whether a relation is an equivalence relation? That to do that, or to determine whether such a relation is an equivalence relation, we simply check whether this relation is reflexive, symmetric, and transitive. So let's check these three properties for R1. So for R1, right? R1, is it reflexive? Well, the answer is yes, right? Since uh well since all element small a of A um, we have that A comma A is in R1, right? 1 comma 1, 2 comma 2, 3 comma 3, and then 4 comma 4. Now how about symmetry? So is R1 symmetric? Well, the answer is also yes. Well, to demonstrate this, we could simply draw the corresponding graph. So you see that um, or we simply go through the pairs, right? For example, uh, in addition to the a comma a, we also have that for every a and b uh, elements of a. We have that if a implies b is in R1, then also b comma a is in R1. You could check, right? So 1 comma 3 is in R1, 3 comma 1 is in R1, and vice versa. 1 comma 4 and 4 comma 1 is in R1, and then 3 comma 4 and 4 comma 2. Whereas 1 comma 1, 2 comma 2, 3 comma 3, and 4 comma 4 um, uh, uh, are, are, are all in R1. Now, is it transitive? Well, the answer is yes. You could check this, right? So, for example, we could simply draw the graph to clarify this. So we have 1, 2, 3, and 4. So you have 1 comma 1, 2 comma 2, 3 comma 3, and 4 comma 4. You also have that 1 goes to 3 and 3 goes to 1, the opposite direction. And then 1 goes to 4 and 4 goes to 1, the opposite direction. And 3 goes to 4 and 4 goes to 3. Now look at this. You see that the if you have 1 to 3, 3 to 4, you have 1 to 4. So you have this corresponding shortcut, right? So, or vice versa, if you go 3 to 1 and then 1 to 4, you have 3 to 4. And if you go from 4 to 3, 3 to 1, you have 4 to 1, and so on. So you have all the shortcuts that we need to um, uh, establish to satisfy the transitivity property. Another way to look at this is actually that we will see later, also very useful property, is the fact that if you have an equivalence relation, then you essentially have islands in the graph. So like this is one part, yeah, uh, and then this is the other island. So here in this part, you could go from one element of A to another, uh, and you can always reach one element from another within um, one hop. Now, so you see that R1 is reflexive, symmetric, and transitive. So therefore, R1 is equivalence relation. Now, how about R2? R2 is R1 union the pair, the set containing pairs 2, 4, 2. So clearly R2 is reflexive because R1 is reflexive. R2 is Z symmetric? Well, it is, right? It's symmetric because, because, well, R1 is symmetric and um, and the set that we add containing these two pairs is also symmetric, right? So you see that R2 if you look at the union, then R2 must be symmetry. But the problem is that R2 is not transitive, right? Yeah, why? Well, because you have 2 comma 4 in R2, and also 4 comma 3 is in R2, but we don't have 2 comma 3. So R2, here the answer R2, so R2 is not an equivalence relation, right? Now, so you see these two relations, one is an equivalence relation and the other is not an equivalence relation. And also another lesson to notice that even though you have R1, you have an equivalence relation in R1. When you add some pairs to R1 to get R2, the equivalence property is not preserved. So in order to preserve the property, you must ensure that whenever you add pairs, the any of the three properties, reflexivity, symmetry, and transitivity, are still satisfied. Right, so that's the example, and let's have a look at the exercise. You are given these three relations, determine whether they are equivalence relations or not. For R1, it's a set of pairs natural numbers a comma b such that a comma b is in R1 if and only if 7 divides a minus b. R And then for R2, you have a relation between pairs of positive integers. So it's not between two positive integers, but rather between a pair of positive integer and another pair of positive integers. So the Cartesian product looks like that. So two pairs are in R2 if and only if two pairs a comma b and c comma d are in R2 if and only if a plus d is equal to b plus c. And finally, the relation R3 is a relation containing pairs of integers a comma b if and only if the absolute value of a minus b is equal to 1. So see whether you could determine if these three relations are equivalence relations, and we shall discuss the solution in the next video.